Assalamu alaikum and welcome to lecture number 22. In this lecture we'll continue from the previous topic, that is signal flow graph, and after that we'll talk about the basic structures for IIR systems and the transposed systems. You understand that transfer function or the system function can be represented as polynomials, and we can also express it as in the factored form, or we can also take its partial fraction expansion. So depending on these different forms, we can obtain different architecture for the same system. From the previous lecture you understand that both the block diagram representation and signal flow graph representation of the LTI system are pictorial representation. If we compare the block diagram and signal flow graph, we see that nodes in the flow graph represent both branching points and the adders, whereas in case of block diagram a special symbol is used for adders. Similarly, a branching point in the block diagram is represented in the flow graph by a node that has only one incoming branch and one or more outgoing branches. In general, we will draw flow graphs with at most two inputs because the hardware normally have two inputs. Signal flow graphs are therefore totally equivalent to the block diagrams as pictorial representation of the difference equations, but they are simpler to draw. So for example, we have this signal flow graph and we want to express it in terms of the equation. So by looking at this node, that is W1n, so we see it has an incoming x of n and another incoming signal here is omega W4 times the input. So W1 equals to AW4n plus x of n. Similarly, this node W2n has incoming this one, which is W1, and that's all right. So W2 basically equals to W1. Similarly, for the case of W3n, we have two inputs here, that is input coming here and the input coming here. So input coming here is W2n multiplied by B0, and similarly the other input is W4n multiplied by or scaled by a factor of B1. So W3n can be written as W2 B0 times W2n plus B1 W4n. Similarly, W4n, which is this one, has incoming this one. Okay, so this is W2n. We have a delay element of 1 unit, so that means W4n basically equals to W2n delayed by a single unit, or W2n minus 1. Similarly, because here we have arrow but there is no value on it, so that means it has same value, that is yn has same value as W3n. So we straight away write yn equals to W3n. So some of the variables can be eliminated, so because we know that W4n basically equals to W2n minus 1 and W2n is W1n. So putting the value of W1n, we get AW4n plus x of n, and again AW4n is basically not AW4n, W4n basically equals to W2n minus 1. So that means we can write W2n equals to AW4n plus x of n, and because W4n is W2n minus 1, so replacing here, now replacing this value here, we get rid of the W3n and W1n and W4n. So simply output consists of y of n equals to B0 W2n plus B1 W2n minus 1. So let's consider one more example here to give you further idea and concepts. Let's consider we have this signal flow graph and we need to determine its system function. Now because this is not in the direct form, therefore the system function cannot be written out by inspection of the graph. So first we'll write the equation, and then from those equations we can find the system function. So coming at the this node W1n, so at W1n incoming is W4n, and x of n scaled by a factor of -1 or multiplied by -1. So that means we have W1n equal to W4n minus x of n. Similarly, for the second case, we have W2n that has the input this one, right? That is W1 times alpha. So W2n equals to alpha times W1n. Similarly, for W3n, we have incoming. It has two incoming, right? Two inputs. So one is W2n, and the other one is x of n. Again, note that there's an arrow, but it doesn't carry any number, so that means just it is identity, that is whatever here it will appear here. So that means W3n equals to W2n plus x of n. At node 4 we have the incoming, this one W3n, and you see there is arrow, and on the arrow we have z power -1, so that means this will be 1 unit delayed version of the W3n. So W4n equals to W3n minus 1. Again, for the output we have two incoming values, that is W2n and W4n. So y of n equals to W2n plus W4n. So these are the equations that will be used to find the transfer function or the system function. So let's take the z transform of these equations. So z transform is represented by W1 of z equals to W4 of z minus straight away the z transform, right? So you understand this one for all we find. This is the z transform of the equation. Now again we eliminate some of the variable, that is W1 of z and W3 of z. So we will get, I hope you can express these, that is we can substitute equation 21a into 21b, so we get rid of W1 of z. Okay, similarly equation 21c into 21d. Okay, this is W3n minus 1 and it is W3n. So if we replace these, so we can get rid of W1 and W3 are in z domain we are talking about, so that will be W1 of z and W3 of z. So we are left with this one. So we find that W2 of z equals to alpha times omega 4 of z minus x of z, and W4 of z equals to z inverse W2 of z plus x of z. Now y of z equals to W2 of z plus W4 of z, so replacing the values here we get W2 of z equals to alpha z inverse minus 1 over 1 minus alpha z power minus 1 into x of z, and similarly W4 of z equals to z inverse 1 minus alpha over 1 minus alpha z inverse. So that means y of z equals to this times the x of z. So on simplification we get z inverse minus alpha over 1 minus alpha z inverse into x of z. Now because we want to find the system function, so system function is basically output over input. So bringing x of z to this side, it will become y of z over x of z, and y of z over x of z will be equal to z power minus 1 minus alpha over 1 minus alpha z power minus 1, or you can say unit delay minus alpha over 1 minus alpha times the unit delay. So this is the system function for the system described by this signal flow graph. Okay, so comparing with the standard equation, I hope you understand. We just split it into this and this, and you know that a of n u of n has z transform of 1 minus a of z inverse. So if you compare with this one, so that means you have a of n this, but because there's a unit delay, so we can write it a of n minus 1 u of n minus 1. Similarly, if we talk about this second part, so this is basically scaling factor of minus alpha, so we have minus alpha times, again this one is the z transform of alpha power n, so it will be minus alpha times alpha power n u of n, and because bases are same and they are multiplied, so we can write it alpha power n plus 1. So this is the impulse response of the system, and we can using this expression, we can straight away express it as direct form 1 or direct form 2. So in case of direct form 1, you can see that's the numerator, these are the zeros, so we can say that input is scaled by a factor of minus alpha, and because we have a delay, the input is also delayed, so that's delay by 1 unit, and here we have node, so we get for numerator we have this diagram, whereas for denominator we have again that's the output, so output is delayed by 1 unit, okay, into scale by alpha. So that's the direct form 1 implementation. You understand, direct form 1 implementation is the one in which you straight away write the or draw the figure for the given expression without simplification. So it has zeros followed by the poles. So by comparing the figures, we see that the original implementation requires only one multiplication and one delay, or the memory element, right? So that's the original implementation, and you can say we have only you can see that we have only one delay and one multiplication, whereas the direct form 1 implementation would require two multiplications and two delays, right? So one multiplication here, one multiplication here, one delay here, and one delay here. Now if we convert this to direct form 2 implementation, we would require one less delay unit, but we'll still require two multiplications. So you know, the rational system function can be expressed in a variety of ways. For example, like we have done not so much, but we have just done that we can express it as in the factored form. We can also express it using the express it in partial fraction expansion and so on. So based on those expression, we can find different implementation for the infinite impulse response systems. Also, a wide variety of equivalent set of difference equations or network structures exist. I think that's now clear to you. One consideration in the choice among these different structures is the computational complexity. You understand, we want to have as much less multiplication as possible. Similarly, the other factors, that was the delay or the memory requirement. So we'll also try to find a system that requires the minimum number of delays or minimum number of memory. So I hope you can go through this slide. That's what we have just talked about. So this is the system function, and we want to implement the signal flow graph. For this one, we have done this for using the direct form 1, or we can also do it using the direct form 2 structures. And we see that this one is the direct form 1 structure, and if we interchange the poles and zeros, so that means these are the poles, they will come here, and these are the zeros and they will come here. So we can also write it like this, because we assume that the system, for sure the system is linear, but the assumption here is about the precision, that we say that we assume we have both the system with infinite precision, so they can be. So here we have assumed that n equals to m, that is order of the both poles, and the zeros is same. You understand, if the other order is not same, so the rest, for example, m is greater than n, and in that case the coefficients of the n for the case where they are not equal will be assumed to will be 0. Note that we have drawn the flow graph so that each node has no more than 2 inputs. A node in a signal flow graph may have any number of inputs, but as indicated earlier, this 2-input convention results in a graph that is more closely related to programs and architectures for implementing the computation of the difference equations represented by the graph. So the direct form structures we obtained were directly from the system function h of z, written as ratio of polynomials in the variable z to the power minus 1. We can also express h of z in factored form, right? So factoring the numerator and denominator polynomials, we can express h of z in the form like this one. So here the f of k and c of k are respectively first order factors for zeros and poles that are real. I hope you understand by the term real that it consists of the imaginary parts are 0, so they are real. Whereas the second order factors, that is 1 of g k z inverse times 1 of g conjugate z inverse, or these are the zeros, where these are the poles, and they are of course the second order, right? So the second order factors represents the complex conjugate pairs of zeros and poles, and here we say m equals to m1 plus 2m2, right? So the order of the zeros, and similarly order of the poles is n1 plus 2 times n2. So this is the order of the pole. This represents the most general distribution of the poles and zeros when all the coefficients, that is ak and bk, are real, right? So in the original expression, you understand, when we express h of z as a ratio of polynomials, so there we have ak's and bk's. So if those coefficients are real, then this distribution will be acquired. So by combining the pair of real factors and the complex conjugate pairs into second order factors, the resulting system function is this one, that's b naught k plus b1 k z inverse plus b2 k z power minus 2, and similarly these are the values for the poles or the denominator factors. So the individual second order sections can be implemented using this. Each second order section has 5 consecutive multipliers. Ns is the largest integer contained, right? So we have ns, and ns equals to n plus 1 divided by 2. So this symbol indicates that we will take the largest integer. For comparison, let's assume that m equals to n. You understand, if they are not equal, so simply the coefficients for the higher order will be 0. So we assume that m equals to n, and also we assume n is an even integer, so that ns equals to n by 2, and we get the exactly an integer. Then the direct form 1 and form 2 structures have 2n plus 1 constant multipliers, while the cascade form structures suggested by equation 30 has 5n by 2 constant multipliers. For the sixth order system, as shown in figure 18, we'll see on the next slide, we require a total of 15 multipliers, while the equivalent direct form 1 and form 2. For the sixth order system that you'll see on the next slide, we require a total number of 15 multipliers, while the equivalent direct forms would require a total of 13 multipliers. The difference equations represented by the general second order sections are of the form as shown here. The input-output nodes are represented by y of k. So for example, y of naught represents the input, which is this one, whereas these are the intermediate nodes. This is y1 node, y1 of n node, this is y2 of n node, and this is y3 of n nodes, and so on. So generally the output nodes we represent by, because you have done the in the previous lecture, you know that we have 3 types of nodes, that is the source or the input nodes, the output nodes, and the intermediate nodes. So the input output are represented by y of n, whereas the other nodes are represented by w of n. So we can write w of k n equals to a1k w k n minus 1 plus a2k w k n minus 2, right, and so on, where k is 1 up to ns. Similarly, y of k equals to b naught k w k n plus b1 k w k n minus 1 plus w b2 k w k n minus 2, and so on up to for k running from 1 up to ns. Now in this particular example we have sixth order system, so we have so for the sixth order system we have ns equal to 3. So to find the expression for this node, that is w1 of n, we can write we replace k by 1, so we can write w1 of n equals to a11 w1k n minus 1 plus a21 w1 n minus 2 plus y of 1 minus 1. So you understand, by replacing k with 1 we get the values for this node, and I hope you understand how it is calculated. So you see there's 1 unit delay and scale by a11, so 1 unit delay and scale by a11 plus 2 unit delay and scale by a21, and plus the input signal, which is y1 minus 1, y of 1 minus 1, which is y of 0. So y of 0 is basically x of n. So similarly you can go for the second node, that is w2k, and you replace just k with 2, so you can find the value of the second, third, and so on. So just you can plug in the value for the k and you can find the outputs for the corresponding nodes. So I hope this clears the idea. So let's consider an example. For example, we are given a system function that has value equal to this one. So because all the poles and zeros are real, so that means we can cascade the structure with the first order section which will have the real coefficient. If the poles and or zeros were complex, only a second order section would have the real coefficients. Okay, so implementing it or drawing the signal flow graph, we see we have a 0 at 1 plus z inverse. So this is the 0, so we have z inverse, and because they have scale of 1, our coefficient, this has coefficient of 1, so it is scaling by 1, so we normally do not mention here. Similarly for the 1, so this is for the first part. Then we have the pole at 1 minus 0.5 z inverse pole factor, so that means we can write it like z inverse, and clearly you can see we'll scale it by a factor of 0.5 because this minus in the formula. If we had 1 plus 0.5, then we'll write minus 0.5. so I hope this gives you understanding. This is for the first pole 0 factor. Then for the second one, we have, again, because both the zeros are at the same location, so we have the same diagram as here. So for the poles we have z inverse and 0.25 scaling. So that's the implementation using direct form 1. So to implement the direct form 2, we interchange the poles and zeros. So this is 0, this will come this side, and this pole, this will come this side. And again, because we are having a unit delay, so we'll get rid of 1 unit delay unit, so that means we'll reduce the memory requirement here. Again, for the second case, we do the same and we save a memory of 1 unit. So that's the signal flow graph representation for the direct form 2 sections. So you understand we have different expressions for the rational system function. So we can express it as in z inverse bk z inverse over a, right, or ak z inverse, and we can also express it in terms of the factors. And you see, using these different expressions we can construct different structures for the LTI system. Now the third structure we are going to consider is the is obtained by expressing a system function as a partial fraction expansion in the form of h of z equals to k running from 0 up to npckz inverse plus. I hope you have understanding of this one, because while doing the z transform we also considered how we can represent or express the partial fraction expansion. So I will not go into much detail here because we have given a lot of time there when we were doing it. So that's the expression for the system function in terms of partial fraction expansion. So we have the first term only when we have more zeros than the poles, or we can say that m is greater than n. So if this is not the case, then the first term will be eliminated. So we're left with these two. So we have summation k running from 1 up to n1. The second term has the second order complex conjugate poles factors, right? So n will be equal to n1 plus 2 times n2. Also, the other important thing is if the ak and bk in the original system function are real, then all the coefficients these, that is capital AK, which is here, bk, which is here, ck, right? Remember, this term only exists when number of poles are greater than number of zeros are greater than number of poles. And ek, these all will be real. The system function can also be interpreted as representing parallel combination of first and second order IIR system with NP simple scaled delay paths. So that means if we express the system function as a partial fraction expansion, in that case the resulting architecture will be the parallel form, right? And the values that represent ck, this one, they will be simply delayed and scaled things that shortly we will see this one, right? Because we'll have a graphical representation for this one. So alternatively, grouping the area poles in pair, we get h of z summation k running from 0 up to np ck z inverse as a k plus summation k running from 1 ns and this form, right? So we are grouping the real poles in pairs. So this is the block diagram representation. So you can see this is basically the term that contains the ck, the first term from the after the equation from the left side. So these are the different sections. Okay, so you can easily see that if you compare with the previous one where we represented the system function as cascade, so in that case we as factors, so the factoring the system function resulted into cascade form, and cascade form means there we had something like in series, like for sections here, then followed by next and so on. Like we take the example of the sixth order system where we had two second order here, then one second order here, then followed by another second order sections, and followed by another second order section. So that's why we call them cascade, because they are in series. So expressing the system function in partial fraction form, we obtain basically the parallel. So you understand, we are just simply adding all the sections here. So again, like we did the expression for the intermediate node, so I think that's quite straightforward. Again, that we'll have a wkn, that's a node, and it will be equal to a1k wkn minus 1 plus a2k wkn minus 2 plus xn, and k run from 1 up to ns. Again, for the input output for the output nodes, we write y of k n equals to e naught k wkn plus e1k wkn minus 1, and we have k running from 1 up to ns. Again, you understand ns is basically uh, n plus 1 divided by 2, and the largest integer we obtain from n plus 1 divided by 2, that is the ns. So the overall output will be equal to y of n, and that will be equal to summation of the individual units, right? So I hope that's quite straightforward. So let's take an example for the parallel form. Now we have system function given as this one, so we can split it uh, or we can expand it using the partial fraction expansion, and we get this equation. So simply that's quite straightforward. So we can say that because the first term is just the scaling, so we have input and that's scaled and it's coming here to sum. Then we talk about the second term. So again in second term we have direct form 2 implementation. So first this diagram is corresponding to this expression. So we have 8, so that's scaling by 8. Then we have minus 7, so you see input scale by a factor of minus 7, then plus 8 z inverse. So this is z inverse, you understand this is direct form 2 implementation. So we just you understand by we have different implementation. One of them is direct form 1 implementation, where you can just by looking at the uh, system function you straight away implement it. In that case you need many, or it requires a lot of extra memory in comparison with direct form 1. In case of direct form 2 you implement poles followed by the zeros, and because in both we need the delay, so the number of delayed elements required are reduced because we are doing the same thing in the poles as well as in the zeros. So that's what we are doing here. So if we implemented direct form 2 implementation, so we have minus 7, okay, and first we'll implement poles and then followed by the zeros. So that's these are the poles. So we have a pole at minus 0.75, right? So the input delayed by 1 unit times 0.75, and again we have another when at the 2 units delay. So because this is plus, it should be negative in formula. So if it is not plus negative here, that means that this is basically minus scaling. Okay, so you have delay 1 unit and minus scaling by 0.125. So these are your poles, and then we come to the zeros. So we have zeros, so just simple scaling. Okay, so we just write minus 7, and then we have scaling after delaying by unit delay. So we have just delayed it unit and then scale it by a factor of 8. So I hope that's straightforward. Again we can represent this equation. So if we represent this equation, then we can see that we have 3 terms here. So the first term is simply scaling, so that's x of n, and that's scaling, and it is summing here. Okay, again the second term, so that's scaling, so that's the scaling. Then for the poles we have delay and scaling by 0.5, so that's delay and 0.5. Okay, for the third term we have scaling by minus 25, so that's minus 25 scaling, and for the poles we have 0.25. So I think that's all. I hope that gives you sense. If you have any confusion, we can discuss in the live session. So the next topic is the transposed form. So in transposed form, what we do, we reverse the direction of all the branches in the network while keeping the branch transmittance as they were. So also we reverse the roles of input and output, so that the source node becomes the sink nodes and the sink node becomes the source node. For a single input, single output system, the resulting flow graph will have no effect, or they will be same as the original graph if the input and output nodes are interchanged. So for example, we have a system that has a system function equals to 1 over 1 minus a z inverse. So the signal flow graph for this will be as shown here. Now to transpose this one, the inputs will be outputs and the output will be input. So that means this point will become y of n and this will become x of n. Again, the directions will be interchanged. So arrow points to the left side, so it will point to the sorry, arrow points to the right side, so it will point to the left side. So similarly, the arrow is downward, so it will become upward. Again, the arrow is left side, so it will become right side. So you can see for a single input output, it doesn't change. Except you can just say that here we scale first and delay it afterwards, whereas in the original case we delay first and scale it later on. So if a signal flow graph configuration is transposed, then the number of delay branches and the number of coefficients remain the same. The transposed direct form 2 structure is always canonic structure. The direct form 2 structure implements the poles first, you understand, and then followed by the zeros. In the transposed direct form 2 structure, implementation zeros will be implemented first and then followed by the poles. So that's one of the example, because we have time for the class up, so I want you to go through it, and if you have any confusion, that's quite straightforward thing, we can discuss it in the live session. Okay, Allah Hafiz.